First, the V-ring seal to be tested is mounted on the specimen holder of the test rig. Both the seal and the counter surface are lubricated with the help of a brush. The fitted width, which determines the contact pressure between the seal and the counter surface, is adapted to the operating condition to be investigated. A running-in procedure, which is performed at the highest velocity to be analyzed, is performed to condition the rubber sample and ensure constant fluid film thickness in the dynamic contact. Finally, the actual friction measurements are performed, whose target value is the frictional torque as a function of the fitted width and the rotational speed of the seal. The friction measurement procedure of the U-cup rod seals starts with the assembly of the seal in the cap of the pneumatic cylinder. The inner side of the seal, which is in dynamic contact with the rod, is lubricated with the help of a brush. A cover plate is mounted on the pneumatic cylinder to secure the position of the seal. The lubricant is also applied to the rod surface. After the cylinder pressure has been adjusted via a pressure control valve, similar to the V-ring seals, a running-in procedure is performed to condition the seals and ensure a constant fluid thickness. Afterwards, the dynamic friction between the U-cup seals and the rod is measured as a function of the cylinder pressure and the rod velocity. The numerical modeling of the friction behavior in the dynamic contact of surface textured seals is essential for the prediction of the friction level and the understanding of the underlying friction conditions. In order to compute the friction in both boundary, mixed, and hydrodynamic lubrication regimes, a coupled contact mechanics and fluid mechanics simulation procedure is used. The simulation steps are indicated in the red boxes, while the transfer parameters from one to the next simulation step are shown in the blue boxes. Initially, the seal, fluid, and operating conditions like the seal geometry, the velocity, and the dimple textures are specified. Some of the input parameters, as the seal surface roughness and the fluid viscosity, are based on experimental measurements which were performed in a previous step. Afterwards, a static contact mechanics and deformation analysis of the untextured seal is performed by finite element analysis. The output parameters of these simulations are the contact length, LX, and the contact pressure level, PDC smooth, between the seal and the counter surface. These values are forwarded to the contact mechanics analysis, which is based on the Greenwood and Williamson contact model, in order to determine an initial fluid film height, H. The following fluid mechanics analysis utilizes the Reynolds equation for the identification of the fluid pressure, PF. Both the static contact pressure, PDC smooth, and the fluid pressure, PF, are coupled by an equilibrium of forces in order to calculate the dynamic contact pressure, PC, which is entered to the Greenwood and Williamson contact model again. This process is repeated in an iteration loop until the fluid film height, H, is converged. In the final step, the friction coefficient in the dynamic seal contact is determined with the help of the previously calculated fluid and contact pressure, as well as the fluid film height, H. The decisive output parameter of the model is the coefficient of friction, which is determined as function of the operating conditions and the surface texture. The resulting friction coefficients are further processed in the reduced order model of our holistic design software.